So this is lecture 16 on invariant maximality derivations by Harvey Friedman. Please.
Thank you. Um, okay, last lecture was number 15, and that was on section 6 of this chapter on derivations. So that was on 3.6. And I decided to rework it. I reworked it a lot for clarity. I didn't change any. The characterization is correct. It's still there, but I amplified things, clarified things. And I have now sections 3.1 through 3.6 already on my downloadable manuscripts page. And I'm going to create some uh, revised lecture notes to go on the lecture note page for section 6, 3.6. So that's a very stable shape. It took quite an effort. So now we're getting into, and also, um, I don't know why this format's strange, but maybe I can fix this now, just a second. Yeah. So that's what the book is. Those are the chapters of the book, the names right now. The table of contents for this chapter changed slightly. Uh, Around the level of if you look at uh, yeah, I call this stability of usability. You can look this up in the downloadable. The usability is invariant on if you change the function, like take its inverse or do various things to the function, it'll stay usable. It'll be usable if and only if it's usable with the change. Uh, this is the finite usability section reworked. Uh, I don't want to go over this too much, but it's kind of organized a little better and cleaner, and maybe one more section. Um, I postponed to the end the discussion of where the statement is proved, where this treatment is conducted. Um, and then today we're doing 371, 372, 381, and 382. And this is, of course, the beginning of the main points. Uh, uh, okay, we'll talk about that in more detail. Basically, this, which already appears already in the stuff, basically that configuration appears. Uh, yeah, I should put the semicolon in front. Uh, Oh, yeah, you know what? I shouldn't put that in front. I don't want to change notation. The semicolon always goes after the interval. Yeah. This means it's the identity on this interval, and then it just progresses one after the other on here. Uh, so this whole thing is reversed in the reversal. Uh, but we want to consider fragments. So this fragment is proved in Zermelo. This fragment is proved in Zermelo. This fragment is proved using just the cardinal omega 1, and this one is proved just using the cardinal omega 1. I mean, this is the first step right here. Now, inside here, I may have some additional results, of course, with more refinements. And then the idea is that in the later parts of chapter 3 are more general results about generalities about what the functions don't have to be just from here like this, more general things, and they have to be organized. There's a lot of open problems, things I don't understand yet here. Uh, all right, so now let's start. So now that we've given a clear, necessary, and sufficient condition for usability of finite functions within actually strong exponential function arithmetic, the S means iterated exponentiation, iterated. We turn to infinite F. Obviously, every identity function is fully usable because if F is an identity, then every uh, subset is. This is, let's fix that. Yeah. So identity functions is true. Just I'm just remarking it's trivial. So what's just beyond identity functions conceptually? Well, the almost identities. So that's a category. ID of X is the identity function on the set X. Remember, everything's one-dimensional here in terms of the of what you're using. An almost identity is a function of the form IDX union H, where H is a finite function. That's what an almost identity is. And we write psi L for the family of all strictly increasing almost identities. Now, if you remember, we proved some time ago that in this subject, the only functions that are usable are strictly increasing. So we only really care about the strictly increasing functions. So hence psi L, strictly increasing almost identity. Actually, psi L, I don't know really why I called it psi L. I think I should call it psi, strictly increasing almost identity. Do I want to call it psi A? That's not pronounceable. How about psi L? What do you think? I think I'll call it psi L. Almost, no, almost identity, almost L, psi L. All right, let's just call it psi L. Strictly increasing almost identity. So the AL stands for almost. All right. Strictly increasing is required. Psi L is surprisingly deep from the usability perspective. The current development of invariant maximality is entirely restricted to psi L. Right. Note that there are continually many psi-Ls, and there's a kind of arbitrary complexity involved in considering arbitrary psi-Ls. However, this arbitrary complexity in psi-Ls is severely limited in that it is only in the form of an infinite subset of the interval. This is, of course, rational interval, and doesn't involve any complex action of the function. For the purposes of tangible incompleteness, we still want to restrict the tangible psi-Ls. So recall the rational intervals we used in section 3.2. These are intervals J contained in Q so that with extended rational endpoints. Henceforth, when we write J with or without subscripts and superscripts, we mean a rational interval of positive length, unless indicated otherwise. Okay, so there are no degenerate intervals unless indicated that. All right, so no, okay, so psi L of J is the family of all strictly increasing functions ID of J union H, where H is finite. Now, even psi L of J, where J is -1, 0, is surprisingly deep for usability. The entire section 3.8, which we're going to get into today, involves many levels of set theory, including well beyond ZFC, living entirely in psi L of -1, 0. All right. So, in other words, if I just look at finite functions, if I just look at the identity function on this interval, -1, 0, together with a finite function, I get already extremely deep phenomena where levels of set theory are involved. All right. But more generally, you can have a finite number of intervals J1 through Jn and consider psi L of J1 through Jn, which is the family of all strictly increasing functions, ID of J1 through Jn union H, where H is finite. And that's even more difficult. Usability in psi L of J1 through Jn creates some more challenges and is the natural stopping place for this book, because that's already at the moment a little too difficult. All right, now there's another way to approach this, which is the order theoretic functions. Recall the natural class of order theoretic functions, which was defined in the section on core mathematical background. Oh, no, I'm sorry. It's part of core mathematics, yes, but I defined it in this section, chapter 3. Yeah, with various characterizations given by theorem 329. In other words, I characterize the order theoretic functions in many ways. Here we identify a function with its graph. We now show that the approach in sections 3.71 is the same as using order theoretic functions. There's an equivalence there. So let F be order theoretic. Then I claim that there's intervals J1 through Jn and finite set E such that the domain of the function is J1 through Jn union E. J1 through Jn E are pairwise disjoint. For all I between 1 and n non-inclusive, the maximum of ji is less than or equal to the minimum of ji plus 1. In other words, the functions are moving to the right. I mean, excuse me, the intervals are moving to the right. Intervals moving to the right. And the function f is constant or the identity on each ji. So this is a basic theorem. You can use quantifier elimination to do this. It's actually not hard to do it with quantifier elimination. I think I'm going to put a proof in there. I am going to put a proof in the manuscripts of this fact using quantifier elimination for less than. All right, so we have the following theorem. If you have a strictly increasing order theoretic function, then it looks like this. Okay. Now, when I wrote it before, did I just repeat this? Let's see. No. This is a general characterization when it's purely order theoretic. This is a general thing. This is a characterization of all order theoretic functions, even if they are not strictly increasing. And then the strictly increasing ones we're particularly interested in. So the strictly increasing ones have, there's no change really, except this is the change. That it has to be the identity on J1 through Jn. It can't be constant at various places, right? Okay. So what I'm saying it basically is that the strictly increasing order theoretic functions are the same as the psi L of J1 through Jn, the various psi L of J1 through Jn. Okay. And the goal of determining the usability of order theoretic functions is the same as determining the usability of the statements of the various psi L elements, usability of the elements of the various psi L of J1 through Jn. And that is, although I know I know a fair amount about this, it's ongoing research to do better. A goal, an important goal would be to actually characterize exactly what they are. Just like I characterized the finite functions, I should be able to, maybe I can characterize the psi-L functions. All right. All right. Let's get into this configuration, these functions. The identity, this function is the identity on here, and map zero divided by n goes to 1 over n. 1 over n goes to 2 over n, and so forth to n minus 1 over n goes to n over n. So that's the function. This covers the reversal. In other words, we know that this is hard. We know that we can reverse that this is usable. But we're actually going to, and we're actually going to prove this from large cardinals. And I've done this now many times over the years in one form or another, uh, adapting to the current notation, which is now streamlined very well. Uh, so I've given this proof using the large cardinals, and then I reversed it. But now this section 3.8 is going to be involved in fragments, but no reversals. So there's no reversals here. Uh, the only reversal in the book is the one that we did for the whole function. All right. Okay, so this just reviews the definition of this. All right. So the very first start is the finite case when we don't have an interval. But this is done completely in section 3.6, on the finite usability. And so we proved that this is fully usable, with no set theory involved. And this is the general case. This is a general case of where, all right. So another thing that I did, yeah, this is a special case of what was actually proved uh, in terms of full usability. Yeah, this is not the whole thing, but this is what you want to say if you just talking about fragments of this, fragments of the thing. All right, so we just got rid of the interval and did this, and you can go all the way to the end, n over n. At one time, I actually thought, there is a proof that uses more than just basic arithmetical things. That actually uses that I thought might be independent of PA, but I was wrong. This actually has a better proof, and it's clear from the section on finite usability. All right. Now, I want to talk about this today. Um, and I want to do some fair amount of details. This is the first case where there's a really serious use of set theoretic methods in order to prove one of these things. This is the simplest situation. And it's very pretty. It's -1, 0, semicolon, 0, comma, 1. Again, I'm not claiming a reversal. See. Uh, all right. So actually, it's more convenient to do this with the axiom of choice. So what we're going to do is prove this well, ZFC minus power set, you're familiar with this. ZFC without the power set, but ZFC without the power set plus power set of omega exists. I don't say exists, I just put it there. And that's the system ZFC minus power set plus the power set of omega exists. All right, now we're going to give a proof that this is fully usable. Uh, we're going to give a proof that this is fully usable in ZFC here. I don't know how to prove that I don't know how to prove it's usable in ZFC minus power set without the power set of omega. There's some avenues of techniques that I have to see if there's a possibility that I could reduce this down. But right now, the natural proof is using the power set of omega. All right, so we fix K and R in an order invariant E. This is our usual order invariant constraint, right? And we want to prove that there's a maximal root, R root. There's a maximal S such that S to the R is contained in E. S to the R is contained in E, which is invariant with respect to this function. That's what we're doing. All right. So first thing we do is we define. It's important to define some spaces. We have a tower of spaces of length omega 1, omega 1 plus 1, actually. There's a top one, T of omega 1. And T alpha is alpha cross 0, 1. And recall that's always the rationals, that interval. Union this top point, alpha 0. Union the top. It's important to do this. It looks a little strange, but this is important. All right. So we order it lexicographically. So this is the lexicographic order on T omega 1. So the ordering is alpha P is less than beta Q if and only if alpha is less than beta, or alpha equals beta and P is less than Q. So this is a lexicographic ordering. Now we're going to want to perform transfinite recursion on this space. Deterministically, we want to do transfinite recursions deterministically, and we need a convenient well ordering of T, not T of 1, T of omega 1 here. Fix this. All right. So so in order to give this well ordering, so this is not a well ordering. This is dense, right? This is a dense ordering. All right. In order to do this, we enumerate effectively, use any effective 1-1 enumeration of this interval in the rationals. Yeah, less than double star. Less than double star. This old thing was less than star. Less than double star is the ordering given by alpha P1 is less than beta Pj. Alpha Pi is less than beta Pj if and only if alpha is less than beta. Or alpha equals beta and I is less than j. So this is the lexicographic ordering again, but this time, instead of using the inherited order of rationals over here, instead of using that, we use the ordering that comes from here. Okay. All right. So that's a well ordering, right? Because we're taking the product of a well ordering with another smaller well ordering, right? Copy of omega, in fact. Okay, less than double star orders. Now, we want to extend this order to order k-tuples. K-tuples, not just one tuples, k-tuples. So x1 through xk is less than double star y1 through yk if and only if the max under less than star is less than the max under less than star. Or the maxes are equal, and lexicographically, the second one is bigger. In other words, there is an I such that xi, such that we have equality before I, and then after that, and right after that, we have inequality, right? It's a lexicographic thing again. Okay. So less than double star is just canonically extended to k-tuples of pairs. Okay, now less than star is a dense, so we can summarize this. Less than star is a dense linear ordering on T omega 1 with left endpoint 0, 0 and right endpoint -1, 0. And it's not a well ordering, of course. Less than star is a well ordering. I'm sorry, this is less than double star. Is a well ordering with left endpoint 0, 0 and right endpoint -omega 1, 0 as before. Less than double star is a well ordering on T omega 1 to the K with left endpoint 0, 0 through 0, 0, K copies, and no endpoint. Uh, right endpoint. Sorry, not no endpoint. Right endpoint. Okay. So I'm saying something silly. Right endpoint, period. I don't know why I am actually doing a set here. It's silly. Oh, and right endpoint, and I did want to say that this set, the set of all, yeah, I'm doing disservice here. The set of all alpha, yeah, and this is the right endpoint. Now another set, the set of all alpha 0 such that alpha is less than or equal to omega 1 plus 1 is a closed set in less than double star with the greatest element. Okay? You should be able to see that, right? Because when we pair with 0, that's the first in that category, you see. So this is pretty easy to see. Now we start off this whole thing with an order invariant subset of KR space. But we want to switch the order invariance to a different space, to a more complicated space. So I switch it to T omega 1, which is a perfectly fine linear ordering, KR space with respect to that linear ordering. See? All right. So how do you transfer from an ordered invariant set in one one linear ordering to another? Well, you do this way. You ask for it to be order equivalent to something. All right. Leave that to you. All right, so now we've got that set up. We want to define what we mean by the E star greedy S. So if you recall, when you want to build maximal solutions to a order constraint, in other words, a maximal S contained in T omega 1 to the K, the most common way to do that is by induction or transfer induction, and you want to do it in a greedy way where basically you're throwing stuff in if you can. So this is the encapsulation of this in common set theoretic terms. We define S with the following condition. X is an S if and only if S restricted to the predecessors of X, union singleton X to the rth power is contained in E star R. And S alpha, we can take a section of it. S alpha is equal to S intersect the space T alpha of K. So you're putting something in S just in case you can, just in case if you consider all the other things you put in earlier, and if you can tack it on and you're still all right, then you put it in. That's what this means. And that's the E star greedy. Okay, now, just as an exercise, there's a unique E greedy S. In other words, this is a legitimate definition. And that's proved in the usual way. You, for each point, you consider a function that works up to that point, and you prove by transfer induction that at every point, for every point, there's a unique partial definition that goes that high. And then you prove they're all cohere, and then you're done. Okay, so that's how and uniqueness is if you have this definition, you just take the least place at which they differ, you get a contradiction. Okay. Okay. Now, what we want to do here is we want to use this greedy construction of length omega 1 and finally pull it down into the rationals. And I put some care into how to set this up. So the first thing you want to do is prove that there's a countable limit ordinal lambda and an elementary substructure of T omega. So you actually want to look at this structure. You want to take this structure very seriously. It's the space, the entire space on of length on omega 1. If you remember, it has a highest point, which is the ordered pair omega 1 comma 0. And I look at this structure, T omega 1 less than star, less than double star. For technical reasons, it's good to enrich this structure to have these basic things that we use in the subject, okay, NS. Okay, and how do you do that? Well, this is a classic thing. You take an elementary substructure. Now it might have all kinds of gaps. You enclose this in a place with no gaps, and you make sure you take an elementary substructure that contains all that stuff that ruined you having any gaps, right? All that stuff in there. You make sure that the next elementary structure contains that hunk of stuff, and so forth. Yeah, and the point is, at the end, you will have covered everything, and you take the union, you will get an elementary substructure because the union it's closed under limits, and this should be formatted. Let me just a second here. Here we go. Yeah, so this is a standard kind of construction. Yeah. So you just use an omega chain. You don't need a transphonic chain. You just need an omega chain for this. Um, yeah. But I mean, the thing is, you have to bear in mind that when we take these elementary substructures, we have the high point omega one is still around, or could be, or likely around, could be around. That in other words, omega one comma zero is still around. It's just that the other stuff lower down is smoothed out now, doesn't have gaps. That's what we're talking about. Okay. Now, there's an embedding, there's an important little function. It's important to have a notation for this, and it simplifies the discussion. Namely, if I have something, a tuple, uh, and it mentions omega one. Now, the only one it can mention is omega one is omega one comma zero. It should be mentioned. That's all. But I have the function. Uh, Now this is a function from k tuples. Be careful. This is a function from k tuples, and uh, so when I wrote a second omega one, that's not quite right. I should write zero. Yeah. Yeah, we're going to add the pair, this ordered pair. Right. Uh, it's just defined as follows. Replace all coordinates that happen to be this exception by lambda zero. So we're just going to list wherever we see omega one, excuse me, whenever we see omega one, we reduce the omega one down to lambda. Because remember, the only way we can see omega one here is if we're looking at the pair omega one comma zero. Okay. All right. Now, um, I claim the following. If I let B and lambda be given by lemma 3823, so let's take a look at what that is here. In other words, this elementary substructure that doesn't have any gaps, this gap-free elementary substructure that only has the one giant gap that goes all the way up to the omega one number. that I can arrange it so that B and S agree on lambda cross 0, 1 union. Yeah, I think I did this again. This is wrong. Okay, this is pair. Yeah. And pi of B and S agree on T lambda. Okay, those are the two things. That's what you get out of this elementary substructure construction. You get these two facts, 1 and 2. And then as a consequence of those two facts, 1 and 2, as a consequence, when one gets this crucial piece of information, that if X is in T of lambda, then X is in S if and only if pi inverse of X is in S. In other words, X is in S if and only if uh, when you reduce the omega ones down to lambda, that's in S. All right. And this is a technical little thing. I don't know if it's useful to do this, but the idea is that we're going to use the fact that this is the greedy construction in order to prove this. See, what's happening is I have this greedy construction, and I'm taking elementary substructures of this greedy construction, and you want to kind of prove that there is an elementary substructure such that greedy construction is very similar to the greedy construction that you're making. The greedy construction, yeah, that the elementary substructures, when you start to look at what the greedy construction looks like in there, is the same as what it looks like in the full structure. All right, so this is all nice bookkeeping that's documented well. And now look at this thing. This has a certain character that we like a lot. It's a kind of invariance, right? But we're in the transfinite world. We're not in the rationals. So we have to be careful what we're doing. So that's to prove that fact. Okay. And now we've finished the proof because with the following idea, if you look at T omega 1 less than star. Now this is the non-well-founded one. If you look at T omega 1 less than star, this single point, lambda 0. Remember, the points here are pairs. It's important to remember. Points here are pairs. And S, that this structure really has the ingredients of invariant maximality. In other words, in this structure, S is actually maximal with respect to the order constraint E, the order invariant constraint E. That's a first order statement in here. That's the first order statement in here. And this transfer that we proved up here, this transfer involving pi here, this transfer is statable and true in this structure. All right. Where's the invariance? See this thing here. This is a first order statement. You see, in the structure that we're looking at, this is a first order statement. So in other words, we have a kind of invariant maximality that we've established already in here. Of course, it's in an uncountable setting. It's not the rational version we want, right? But it's in the transfinite world. And you can state that in a first order way about this structure that I've highlighted. And if you do that, you will look for a countable elementary equivalent. You don't need a countable elementary substructure. This time you just need a countable elementary equivalent structure. If you do that, it will look like this. And D will be a density ordering with left and right endpoints. And you'll have some intermediate point C. Okay. And you have a different S prime, right? And now, since this is a dense linear ordering with endpoints, it looks like this. Okay. So the maximality is first order, and the invariance that we're talking about is first order. And so we actually get here, we actually get in here the same thing. In other words, we get that S star is maximal, and that in the appropriate sense, and that it's invariant in this appropriate sense, just by transferring. So what we did is we took the problem of proving that this is fully usable. We took the problem of getting a maximal thing, which is invariant with respect to this. We blew it up into a carefully chosen uncountable space where we did an elementary substructure construction, and we proved that we actually could get maximality. We actually got greedy maximality, which is even stronger, that we could get through the greedy construction, we could get a maximal S, and which is invariant with respect to this pi function, which replaces 1 by 0 and 0 by 1, but in the original transfinite structure, it replaces omega 1 by lambda and lambda by omega 1, just that there is a countable lambda like that. And so that's exactly what we want to know in the transfinite structure here, so that we know that we have a structure like this in which it holds with a suitable S. I think maybe I have to be careful that I don't reuse. Oh, the S, I did this. I put a star in it, S star. And so we're done. Okay. And now I kind of did this in detail and bare bones in some sense, because it's the actual first place in which you have to do something transfinite in this subject called invariant maximality. Is the first place where, and it's interesting to see what the minimum use of set theory is for such a thing. And this appears to be the place. I mean, again, I haven't done a reversal. to see if there's or even try to dig in and make the proof much simpler. I did talk to somebody about this. Yeah. Okay. So yeah. Okay. So just one more summary. We blow it up to a transfinite structure. We then have a corresponding notion of invariance, except it's in a transfinite setting. We build a natural maximal invariant. We check that we've built an invariant maximal set in the transfinite side by taking the most obvious natural maximal construction, which is the greedy one, and then analyzing the greedy one in order to prove that it's suitably invariant in the transfinite setting. And then we go to a countable elementary uh, equivalent situation. We will also find the same phenomena. We'll find maximal invariant set, which is what we want to find. So that's the general technique in this very basic setting. All right, I'm done. Thank you.